Welcome back. We're gonna go over example number 2. In this example, we're looking for the interval where the graph is increasing or decreasing. Along the way, we're also gonna find the critical numbers. And so let's begin. So the given function is negative 2x cubed plus 24x squared minus 72x plus 2. So for these functions, there are three important open intervals, negative infinity to a, and from a to b, and from b to infinity, where a and b are going to be the critical numbers. So this is already kind of set up for us in this context to help us find these intervals, right? So let's begin by finding the critical numbers. So in the previous video, we talked about how to find critical numbers. The critical numbers are defined to be the values of x in the domain of f for which they make the derivative of the function be zero, or they is where the derivative is undefined. Again, we have to remember that this value of x must be part of the domain of f. All right, since this is a polynomial, polynomials domain is all real numbers. So any critical numbers that we find, any values that we find this way, by definition, will be critical numbers. All right, so let's begin. So to find the critical numbers, we're gonna begin by first finding the derivative, right? Because that's how we define the two cases. We can find the derivatives whenever the derivative is zero or undefined. So begin by finding the derivative. So critical numbers, we're gonna find them by taking the derivative of this function. If we notice here, we have negative 2 times x cubed. So by using constant multiple rule along with power rule, we end up getting the negative 2 by bringing down the power, and multiplying by 2 is going to be negative 6 times x, and then subtract 1 from the power. That becomes a square. Plus, then we have 24 times x squared, and again, we're going to use the power rule and the constant multiple rule. So we have 2 times 24, that's 48 times x raised to the first power, because we subtract 1 from the power. But again, we're not going to write down the power 1 because that's not common for us to do, but you can write it if you want to. And then minus the derivative of 72x. So that is going to be, when we have 72x, the derivative of this is just going to be negative 72, right? We just pretty much almost just drop this value of x, right? We can define that to be the linear rule. And then plus 2, the derivative of plus 2 is just going to be 0, but we're not going to write the 0 there. So we have found the critical numbers. In order for us to find whenever this is going to be 0 or undefined, the best way for us to do this is by factoring. So let's go ahead and factor this out. Factor as much as you can, right? In this case, we can see here that the negative 6 is a common factor in all these three in these three terms. So minus 6 times whatever's left behind. So we're gonna have an x squared left behind, minus 3 minus 8, sorry, minus 8x, and plus 12. If we notice, how we know that is because negative 6 times 1 gives you negative 6. Negative 6 times negative 8 gives you positive 48. And negative 6 times 12 gives you negative 72. All right, so we found that factorization. We're going to continue factoring. Now that we have this trinomial, we can try to now factor it into the factors of two binomials. And we can kind of guess that the factorization for this will be x and x here. So we just have to guess, or have an educated guess of the two numbers. So two numbers, when you multiply, gives you positive 12, but when you add them, gives you negative 8. That is negative 6 and negative 2, or minus 6 and minus 2. So there you go. We were able to factor. The reason we're going to factor this out is because we're going to find the critical numbers. And this is going to happen whenever the derivative is 0. So here we go. So first case would be when the derivative, for the derivative to be 0, right? We're going to set this equal to 0. So we're going to take the derivative and we're just going to set it equal to 0. So minus 6 times x minus 6 times x minus 2 equal to 0. And this will only happen whenever, right? And why we set it equal to 0? Because that's one way we can get critical numbers, whenever the derivative is 0. So we're using this constraint to find the critical numbers. So set this equal to 0 to find the critical numbers. And that's going to happen in two cases. By the zero factor property, this happens when x minus 6 is 0 or x minus 2 is 0. Notice that we don't use the case where negative 6 is going to equal 0 because we already know that negative 6 cannot equal 0. So that's a factor we're not going to use. And then from here, we're just going to add 6 on both sides to solve for x. Add 2 on both sides to solve for x. And that's how we end up getting x equals 6, comma, x equals 2. Now there is another case we have to try, and that is whenever the derivative is undefined. Now we can assure you that this is never going to happen. The reason why the derivative cannot be undefined is because f prime is a polynomial, and this is defined everywhere. So therefore, this cannot be undefined. So there's no critical numbers from here. Nevertheless, you still gotta check, right? So the only critical numbers we found, the critical numbers we found were x equals 2, comma, x equals 6. Right. So now what we're going to do is now this, you can see that we're going to put them in order. And this could be, A is going to be your 2, and then B is going to be your x, B is going to be 6 in this case, according to our intervals that we already pre-set up, right? Now what we're going to do is we're going to find the interval where the function is increasing or decreasing. For this, we're going to derive this testing feature, and that's going to happen. We know that there's a relationship between the derivative and the function. We know that when the derivative is positive, meaning your slope is positive, that means the function is going this way. That means your function, your f of x, is increasing. So it means f of x is increasing. And when f prime of x is negative, that means your slope is negative. So that will be this case. That means f of x is decreasing. So what we're saying here is that we have now a way to actually test this by creating a number line and setting up and breaking down and using the two critical numbers. We're going to use the critical numbers to define when the function is increasing or decreasing. We already know that when x equals 2, the value of the derivative is going to be what? 0. When x equals 6, we know that the derivative of the function is going to be 0 as well. So we know what's happening here. What we wanted to know is what is happening between this, in this region, in this interval, what is happening between 2 and 6, and what's happening after 6. So what we're gonna do here is we're gonna test some numbers. So we're gonna test a number in this side, for example, a number that is less than 2. A number that is less than 2 is 0, right? That's actually a nice number. Actually, I'm gonna give a different color, just so that we can kind of see that these are our testing numbers. And then you're going to choose a number between 2 and 6, any number, but you always try to pick numbers that are easy to compute, so I'm going to use 3. And then a number on the right side of 6, and that is also easy to compute. In this case, we're just going to say 7. So what we're going to do is we're going to figure out what are the values of the derivative here. What are the values of the derivative here? Because if we know what's the value of the derivative, and not necessarily the actual value, we just care whether it's positive or negative. If we know whether the derivative is positive, then we know whether the function is increasing. If we know the derivative is negative, then we know whether the function is decreasing. That's the connection we want to make in this section. So what we're going to do here is we're going to test these 3 numbers, f of 0, f prime of 0, f prime of 3, f prime of 7. So let's write down the derivative. F prime of x is negative 6 times, according to our work, x minus 6, x minus 2. And so we're going to try first f prime of 0. Now I'm going to go ahead and write it out here, set it up for ourselves by plugging in 0. Then we're going to plug in, I'll give a little more spacing here. Then we're going to plug in 3. And then we're going to plug in 7. So we're testing these numbers. And again, all we care is whether the derivative is positive or negative. So we're going to try 0, 2, 3, and 7. So what happens when you plug in 0, right? You place every value in here by 0. Now, the beauty of using the factor form of the derivative versus using this form of the derivative is the following. Because everything is in a factor form, it's going to be very easy for us to actually compute this in terms of sign. Now, this is very informal, but we know that negative 6 is a negative number. We know that 0 minus 6 is also a negative number. And we know that 0 minus 2 is also a negative number. So you see, we have the sign values of the numbers, right? We have a negative number being multiplied by a negative number. That turns to be a positive. This is a positive number. So this turns to be a positive. A positive times a negative becomes a negative number. So we have found that this outcome will be a negative number. So we'll come over here and then type and just write out, oh, this is not negative, negative, negative. Or I can put this in blue. Negative, 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 negative. In the same, with the same argument, we're going to do the same thing for the next one, right? So for 3, type in 3 there, 3 there. Same thing here. We have that negative 6 is going to be a negative number. We know that 3 minus 6 is going to be also a negative number. And we know that 3 minus 2, well, 3 minus 2 is actually positive 1, right? So that's actually going to give us a positive number. Because we don't actually care about the actual value, we just care whether it is positive or negative. We can get away with this. We can get away with it. So we have negative times a negative turns to be a positive. So far, this whole thing is a positive times a positive and turns into a positive. So we have this is a positive value. So here would be positive, 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 positive. Let's continue with the next one. Let's see what happens on the next one. So we have, we're going to plug in 7 and 7 in here. And we're going to try this again. We're going to say what happens when we have negative 6, which is a negative number, right? It's negative 6, but we don't care that it's a negative 6. We just care it's a negative number because all we're doing here is multiplying. 7 minus 6 is positive 1. We don't care about the 1. We just care that it's positive. And 7 minus 2 is also positive. because we're just multiplying, because we have in the factor form, we can get away with just multiplying these. Negative times positive turns to be a negative, and then times a positive turns to be a negative, right? So this whole thing is going to be a negative value. So this will be negative, negative, negative. There you go. So this is known as the testing for the increasing, decreasing. Now what I would suggest here is that you come back over here and try to draw a picture of it, right? So if you think about it, if you have a negative slope, if you have a negative derivative, that means the function is decreasing, like that. So that's how the function will behave, right, in the picture. And then you have 0, that's flat. And then the derivatives increase, the derivative is positive, so that means the function is increasing. So it's increasing for that interval. And then it's flat, and then it decreases, right? And then it decreases over here. So because the derivative is negative, that means the function is decreasing. So when you're writing your intervals, you will know, right, by looking at the picture above, we can determine that from negative infinity all the way to 2, the function is decreasing. So from negative infinity to positive 2, the function is decreasing, and then from 6 to positive infinity, the function is also decreasing. So we have from 6 to infinity is also decreasing. Now because these are two intervals, we want to unite those two intervals to create one single, value, right? Expression of x. We're going to say that these two, if we unite these two intervals, then this is where the function is decreasing. That's how you're going to write it in the homework. And then we're saying from 2 to 6, the function f of x is going to be increasing, right? So from here, from 2 to 6, the function is increasing. Okay, and that's it. So I want to say that I want to say this, and this is very important. You may be thinking about this. What about if we chose a different number, like 1, to test, right? Instead of using 0, we would have used 1. We would use 1. You use 1. You still would have got the same answer. You would have got a negative 6. I mean, a negative number, and a negative number. So no matter what number you pick on this side, you would have got the same outcome: negative, negative, negative. Also, it means the same thing here. If you would have chosen, like for example, 4, you would have got the same outcome: negative, negative, positive. And it does. So what I'm saying here, it doesn't matter what number you choose. It could be a decimal, it could be any number. As long as between 2 and 6, you will get the same outcome.